Hello AMP1 students. Welcome to Anatomy and Physiology 1. I am Deb Weeps. I'm one of the three team instructors for your class this semester. And this is a screencast that is meant to cover some of the basic chemistry information that is required to understand much of the physiology of the body. This is the first in a series of several screencasts that actually reviews prerequisite information that you should have gotten in a chemistry class prior to signing up for AMP. But we understand that students often, sometimes they forget that information, or maybe it's been a long time since you've looked at it. So we prefer to provide these screencasts as a method of reviewing that information. This particular screencast will cover the information that you need to know for study question 1-1 on atoms and elements. The first part of your study question asks you to define the term element. Before I do that definition, though, I want to talk about this term called matter. Matter is anything that occupies space and has mass. What this essentially means is everything that you see in the room where you're sitting right now, anything that you can touch, anything that you can smell, and then some, all of these items are made up of matter. So matter is the stuff that makes up all substances of the universe, to give it a pretty broad meaning. Now, if we take a look at one object in the room where you're sitting, such as the chair you might be sitting in, it's made of several different, it is made up of matter, but that matter that can be seen, smelled, felt, or whatever is made up of elements. Okay, so the chair you're sitting in is made up of a variety of different elements that are chemically put together to make up that chair. So let's define the word element now. An element is the simplest unit of matter. The simplest unit of matter. This means that each of these elements that make up that chair have a particular chemical behavior. When you put them together in a combination, they form a solid chair that you're sitting on. But when you break those elements down into when you break that matter of the chair down into its individual elements, a single element is the simplest unit of matter that still has some type of chemical behavior. This element can't be broken down further by ordinary chemical means. Okay, so it still maintains its chemical behavior that particular element is known for. Now, it doesn't mean the elements can't be broken down further. However, it takes some complicated methods in order to do that. Now, when we take a look at the elements of importance, that's going to involve the periodic table. Now, here we have the periodic table over here on the right side of the screen. This is a simplified periodic table. It only contains some of the known elements. There are actually approximately 118 elements that are currently recognized, but not all of them occur in nature. This periodic table represents the 92 that are found in what we would call natural structures or natural substances, or they occur in nature. The majority of them also occur in the human body. Some of them do not, and that's specified down here at the bottom. The ones with the stars right here that are not listed, these are not found within the human body. Some are more abundant in the human body than others. There are 4 major elements that occur in the human body. Oxygen is one of them. It's represented, its chemical symbol is the capital letter O that I have in red there. Approximately 65% of the elements in your body consist of oxygen. So it's a lot more than you might expect. On the periodic table, it's element number 8. Carbon is also a major element in the human body, 18.5%. Now you don't necessarily need to know the percentages of each of these, but you do need to know which is most abundant and kind of the order of which one's first, second, third, fourth. So carbon is the second one, it's element number 6. The third is hydrogen. Its chemical symbol is the capital letter H, and I'm hoping you're picking up on the fact that I'm putting their chemical symbols in red. It makes up about 9.5% of the human body, and it's element number 1 here on the periodic table. The fourth one is nitrogen. Nitrogen makes up about 3.2% of the human body. It's element number 7. Now there's a lot of other elements on this periodic table, so the next category that we're going to discuss are called the lesser elements. The next group of elements are called the lesser elements. They're still important to the human body and they're required for proper functioning, but they exist in lower concentrations than those first 4 that I just discussed. There's a group of 9 of them. They include calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. Now notice that their concentrations range from 1.5%, which is calcium, down to 0.1%, which is iron. So they exist in much lesser quantities as compared to the major elements, the 4 major ones that I previously discussed. Now there's a third group of elements that are just as critical to the human body as the other ones, but they're required in very, very minute amounts. These are called the trace elements. And the trace elements include chromium, cobalt, copper, fluorine, manganese, molybdenum, selenium, silicon, tin, vanadium, and zinc. Now, I'm not listing any concentrations or percentages for each of these, but just understand that they are required for proper functioning in the human body. Oftentimes they're assisting enzyme function, and we'll talk about enzymes later on and the importance of enzymes, but they're required in extremely small amounts. The next question you want to consider is, what is an atom? We ask you to define the term atom. First of all, an atom is part of an element. Think about an element as many, many atoms all hanging out together. A single atom is considered to be the smallest working unit of an element. By working, I mean that atom retains the chemical properties of the element. So if you looked at an element like carbon, here we show a carbon atom in the diagram. If you looked at the thousands of carbon atoms that exist in maybe the table that's in front of you, if you're sitting at a table, all of those carbon atoms will have similar chemical properties. If you take each individual atom, it'll still behave as the other atoms do within that element. That's why it's called the smallest working unit of the element. Now we need to take a look at the structure of an atom. An atom, as you can see in the diagram on the right of the carbon atom, is made up of certain types of subatomic particles. Protons are found in the centermost area of the atom, and they're represented by these orange circles with the plus sign in the middle of them. All of these are protons. Neutrons are also found in the centermost area of the atom, represented by the gray circles. They have a 0 in the center of each one of those. All of those, well, it's represented that way. They don't actually have it in when you look at it, look at an atom. But anyway, they're represented on this diagram with a 0 in the center. The third subatomic particle is the electron. And an electron is represented by these yellow circles. The electrons are found outside of that centralized location, and each one of them has this minus sign in the middle. Those symbols in the center of each circle represents the electrical properties of these subatomic particles. Protons are positively charged. Let's back up a little. Neutrons are neutral or have no charge. That's why they have a 0 in the representing each one of those circles. And the electrons are negatively charged. That's why they have the minus sign representing in this diagram. Their arrangement is somewhat predictable. The protons and neutrons, as shown in the picture, are found in the nucleus of the atom, or the centralized portion of the atom. You can see them right there in the middle. While the electrons are found at specific distances away from the nucleus. The electrons reside in areas called energy levels. They can also be called electron shells or electron levels. There's a variety of different terms used. I like the term energy level because it represents the amount of energy exerted in that particular location. Now, our diagram shows it in an orbital pattern. It shows how the electrons appear to be, here, let me use this little diagram here, how there's an electron right here and here in this what looks to be kind of a circular pattern that surrounds the nucleus. And my circle's not going to be very impressive, but I'm trying to make a point here. The electrons do not travel in an orbital pattern like that. They don't go in a circular path around the nucleus like the moon travels around the Earth, or the Earth is traveling around the sun, or whatever. It's not an orbital pattern like that. It's a predictable area that's a certain distance from the nucleus. And those electrons are massively moving around in that predictable area. That's what an energy level is. It is at a predictable distance from the nucleus, however. So this red circle that I drew in is the first energy level. The second energy level will be farther, and I'm just outlining this outer orbital. And again, remember, it's not a circular pattern that surrounds the nucleus, but it is a somewhat predictable area at a certain distance from the nucleus. So this energy level is farther away, oops, let's try to do an arrow here, farther away from the nucleus than the first energy level. Okay, so each of these energy levels, because they're further away, think about it, the nucleus has positive protons in it. The electrons are negatively charged. The ones closer to the nucleus are going to be more attracted to that nucleus because positives attract negatives. If the energy level's farther away from the nucleus, it's not held in place quite so strongly and is more apt to have be involved in chemical reactions with another atom the further away it gets from the nucleus. That outermost area is called the valence shell, or the valence energy level. It contains what are called valence electrons. So this would be considered, I'm putting a green circle around this one. Each of these are considered to be valence electrons. They are residing in the outermost valence shell that's furthest away from the nucleus. Now the next question that we're going to answer is, why is an atom always neutral? When a student takes a beginning chemistry course, they typically learn that an atom is the smallest working unit of an element. And the word atom becomes kind of generalized to include any of those smaller particles that are, considered part of the element. In other words, whether an atom has been involved in a chemical reaction or not, people generally use the term an atom, like an atom of sodium when it's all by itself, and an atom of sodium when it's been involved to form salt. In reality, this is incorrect. The word atom always means a structure that has an equal number of protons and electrons. So in a neutral atom, the number of subatomic particles, positive to negative, will equal one another. When we take a look at our diagram to the right, as we pointed out earlier, an atom of carbon has 6 protons, right there, and 6 electrons, right there. We can see them in the diagram as well. We can count up 6 protons or positive structures in the nucleus, subatomic particles in the nucleus, and we can count up 6 electrons in the various energy levels outside of the nucleus. Because the protons equal the number of electrons, so we have the number of positive protons that equals the number of negative electrons. Positives equal the number of negatives, and therefore the charge cancels out. The atom is always neutral. If something occurs and an atom goes through a chemical reaction with another atom and either loses 1 or more electrons or gains 1 or more electrons, now we've changed the situation. That structure is no longer an atom. Once the number of electrons does not equal the number of protons, we now have an ion, not an atom. Because if you offset the numbers, now that structure, that ion, is either going to have a positive charge if it lost electrons, because that means it's lost some of its negative charges, resulting in a more positive endpoint, or that ion will be more negatively charged because it gained electrons. So remember, an atom is always neutral. If it's not neutral, it's now an ion. Now we're going to take a look at characteristics of atoms, and specifically look at this atom of sodium. On the upper right, I have sort of cropped out a small box from the periodic table showing some information that's very helpful to know about an atom of sodium. One of the items shown in that small box is the atomic number. I'd like to kind of outline that atomic number. It's right here, and it happens to be the number 11. So sodium is element number 11. That number 11, which is also the atomic number, represents the number of protons that you find in that atom. It's shown in the diagram down below with the purple nucleus in the center that sodium has 11 positively charged protons. Now this is true for a neutral atom of sodium. It's always going to have 11 protons. It's also true if that sodium gets involved in a chemical reaction and becomes an ion. That atomic number will still represent the number of protons that's in that particular structure, whether it's an atom or an ion. The atomic number also, in some cases, represents the number of electrons, but only represents those number of electrons when you're discussing a neutral atom only. Because remember, the only reason it's neutral is because the number of electrons that are negatively charged are equal to the number of positively charged protons, and that makes it an atom, okay, a neutral structure. So the atomic number, most importantly, is used to represent the number of protons, and that's always. It will also represent the number of electrons if you're talking about an atom that is it's in the neutral state. So the sodium atom has an atomic number of 11. When we look at the arrangement of the electrons in this neutral atom, so we're not talking about one that's been in a chemical reaction now, we're talking about one that's just, it's a neutral situation, so it has equivalent electrons to protons. I want to discuss this a little bit because just because an atom is neutral does not mean that it's stable. Stability has to do with the number of electrons that are found in each of these energy shells or energy levels that are outside of the nucleus. When we look at sodium, the first energy level that's closest to the nucleus contains 2 electrons. That happens to be the maximum number of electrons that you will ever find in that first energy level. So there's 1 of those electrons. Here is the second electron. Oop, that's a terrible circle. Anyway, those 2 electrons, that's the maximum number of electrons you can find in that first energy level. It can't hold any more than 2, and it's found closest to the nucleus. The second energy level can hold up to 8 electrons, and this doesn't matter what element you're talking about. The second energy level can hold up to 8, and that's what we find with the sodium atom. The second level is completely filled, and I'll just use a little dot here to show 1, 2, 3, 4, 5, 6, 7, 8 that are located in that second energy level. So now it's completely filled. There's a third energy level, but now when we add up what electrons are already accounted for, we have 10. 2 in level 1, 8 in level 2. So we only have 1 electron left, and that's what we find in the third energy level, or the outermost energy level. We have 1 lone electron right out here, and that adds us up to 11. That outermost electron is located in what's called the valence shell. The valence shell is the furthest distance away from the nucleus, and it actually makes this atom somewhat unstable, because that energy level prefers this atom really to be stable. It needs to have 8 electrons in its outermost shell. If we have a different number in that outermost shell, as we have here, having just 1, it makes that atom quite unstable. And that atom is more likely to seek out a chemical reaction where it can either donate an electron or pick up electrons to fill this level to 8. Well, because we only have 1 lone electron out here, sodium very commonly gives that away in a chemical reaction to another atom, and that's how sodium becomes an ion. Now, this third level is very important in this case. For sodium, this valence shell is the reactive area. In other atoms, it might be a different outer shell, because once sodium would donate this lone electron, then now its outermost shell would be the second one, and it's filled with 8. When we're talking about these energy levels and how many electrons they can hold, in AMP1 we really don't go beyond looking at that third energy level for the types of chemical reactions we're going to be studying in class. There are energy levels where it becomes a little bit more complicated as to how the electrons are deposited into those energy levels. We will not be discussing that fact. Another number on the periodic table that's of importance is the atomic mass. Atomic mass is shown up here in this periodic table on the upper right. and I just about crossed it out. It says 22.99. That's not a whole number, okay? So let me discuss mass in the first place. Mass is a measurement that some people sometimes equate mass with weight, okay? And that's a little bit of a misleading approach. Let me describe it this way. Let's say you're standing next to a swimming pool and you have a scale right there, and you stand on the scale and you measure your weight, okay? So you have a certain value, you know my weight is such and such. Then you jump into the pool and someone weighs you on using a type of specialized scale, weighs you when you're floating in water. Your weight in the swimming pool is going to be much different than the weight that's recorded when you're standing next to the pool. So that's weight. Mass is a little different because it stays the same. The mass of an object is constant regardless of the environment that it happens to be in. So your mass would be the same whether you're standing next to the pool or you jump into the pool. Now, when we look at these subatomic particles, now this diagram doesn't show it very well, but some of the earlier diagrams represented how the protons and neutrons are much larger in size than the electrons. It's the protons and neutrons that create the mass of the atom. Now, the interesting thing is that not all atoms of an element are created equal. One sodium atom will differ in its mass a little bit from another sodium atom. So what has to occur is an average of all of those sodium atoms. The atomic mass then represents the average combined mass of protons and neutrons in all the atoms of that particular element. And when we add them all up and average them together, it ends up not being a whole number. We end up with 22.99 in this case. Now what we typically do, sorry for that little pause there, I forgot I had added this in here. I love these screencasts. They show all your errors when you're not quite prepared. Anyway, this number, as I said, is 22.99, but for our convenience purposes, we like to round that number up to 23. But I want you to understand it's typically not going to be a whole number. It's going to be some type of an odd number because it's an average. But we're going to round it up for a specific reason. We want to use this information, both the atomic mass and atomic number, to calculate some other information about the atom. At this point, I'd like to take a look at another way of utilizing the information shown on the periodic table. I already told you a little bit about atomic number. I mentioned atomic mass. We can utilize these values to come up with the specific number of subatomic particles found in a single atom of any element. With an earlier slide, I described to you that the atomic number, and in the case of sodium, the number 11, represents the number of protons found in that atom. It also represents the number of electrons, and I explained that as long as you're talking about an atom, which is a neutral structure, the number of electrons will equal the number of protons. Not the case if you've ended up developing an ion, or if sodium becomes an ion. But in this case, we're talking about an atom. So we have 11 protons and we have 11 electrons. The only subatomic try to say that 3 times fast. The only subatomic particle left to determine are the neutrons. I had also mentioned that the atomic mass of this element is the mass of all protons and neutrons found in all atoms of that element. And it's an average taken of all of those, the mass of all of those protons and neutrons. Now let me talk about mass just a little bit more. A mass, one mass unit is the number 1. When we determine mass, I want you to take a look at this box over to the right that shows the size of a proton and the size of a neutron compared to the size of the electron at the bottom. Notice that the proton and neutron are shown larger in size than the electron. This is why they constitute the majority of the mass of the atom, because they're larger structures. So one proton has an atomic mass unit of 1. One neutron has an atomic mass unit of 1. So if we look at our atomic mass right here, 22.99, we can use that number to calculate the number of neutrons in the atom. We already know the number of protons. So what we would need to do is take the atomic mass number, which is both protons and neutrons, and subtract the atomic number from it that represents only the protons when considering those two. Therefore, we're going to look at this mass number of 22.99. We're going to round it off to 23 because it's just a little more convenient to work in whole numbers, and take the atomic mass and subtract the atomic number from it, and what we have left over are the number of neutrons found in that atom. The last part of your study question asks you, what is an isotope? I've been sort of hinting at that with a lot of the previous slides. We have looked at the atomic mass number in different ways. I had mentioned that that mass number is the average of all the different varieties of atoms that make up a particular element, and specifically the number of protons and neutrons within all those varieties of atoms. Well, we're going to take a look at the varieties of another atom, and that's hydrogen. In this diagram, it actually shows 3 different varieties of hydrogen. Let's look at the first one. This hydrogen atom, now we're talking about atoms here, we can see it's represented with a capital H. This hydrogen variety has 1 electron out here in the first energy level. There's our 1 electron. It has 1 proton in the nucleus right there. Okay, so one electron, 1 proton, but it doesn't have any neutrons. Notice it has no neutrons. The variety right next door is still hydrogen. Okay, it's still hydrogen. It is given a name called deuterium, but notice that it's represented with the capital H. It's another variation of hydrogen. Now this one's a little bit different. It has 1 electron in the first energy level. It also has 1 proton in the nucleus, but now we have a neutron present. Okay, we've got 1 neutron right here, okay, that we didn't have in the first variety. The third example that's shown is still a hydrogen atom, but this one called tritium is a little bit different. It has 2 neutrons in the nucleus right here. There's 2 neutrons right there. So what we can see in each of these varieties of hydrogen atoms is that we maintain the same number of protons, and because it's an atom, each of them is an atom, we have the same number of electrons, but we change, there's a variety in terms of the number of neutrons. An isotope is a structural variation of the same element that has differing numbers of neutrons. So each of those atoms will have the same number of protons, same number of electrons as the other atoms, but the number of neutrons will differ among those different variations. So they are all considered isotopes. All three of these are considered isotopes of hydrogen. We could do the same thing when we look at sodium. We've been looking at the sodium atom all the way along pretty much. Keeping in mind that the mass number is an average of all these isotopes, we would have to do the same thing for sodium. If we looked at sodium atom number 1, it might have 12 neutrons, as it did with the calculation we did earlier. But looking at another atom, that one might have 13 neutrons. Another atom might have 11 neutrons. So after we observe many of these different atoms, we would take the average of all of these slightly different masses of protons and neutrons, average it out, and we would end up coming up with 22.990, as we see on the periodic table, or maybe a slight variation of that. Now we end up rounding it up to 23 when we use it for calculation purposes, but this number, 22.99, represents the mass, the average mass of all the isotopes that exist for sodium, all the different variations of those atoms. Well, that brings us to the end of study question number 1-1.